In our previous lessons, we were working with perfect squares, and we were describing that a perfect square represented the area of the square because it came from the side times itself. So our most commonly used perfect squares are listed here: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, and so on. Now, these are the areas of the squares. What would be their corresponding side lengths? So for example, if you had an area of 100, its side length was 10. If you have an area of 81, its side length was 9. An area of 64 had a side length of 8. And so we talked about how we could take the square root of the area to find the side length. And so we gave you your organizer with your multiplication table where the areas of the squares were on the diagonal, they're highlighted. And then to find their corresponding side lengths, we can just look either up or to the left on our table of values. And again, we also have the list for you as well. So if you'd like to use your organizer to help you through this, you're welcome to do that. Over time, you'll just kind of have these perfect squares memorized, and it will make things a little bit easier as you're doing your simplification. So for example, if we are going to simplify the square root of 32, we want to ask ourselves, well, where does 32 fall within our perfect squares list, right? The areas of the squares. Well, 32 falls between 25 and 36. So I'm going to start here with the next lowest value and ask myself, can I take 32 and divide 25 into it and get an integer, a whole number answer? And we know that it's not going to work. Then go to the next one below that. Can you take 32 and divide it by 16 and get an integer, a whole number answer? And we can. That would be 16. So here we have the square root of our perfect square area, 16, and what would be left over? A 2. Now, we know that since 16 is a perfect square, what side length created that area? That side length is 4. And we can't do anything with 2, that's not a perfect square, so we leave it as is. So the square root of 32 simplifies to 4 square root of 2, or 4 radical 2. Now, if we wanted to look at the square root of 12, we take the same process. So again, we're going to say, all right, where does 12 fall on your area list? Well, 12 falls between 9 and 16, so we're going to start with the 1 below that. Can you take 12 and divide it by 9 and get your integer answer? No, we can't. So we go to the next one. Can we take 12 and divide it by 4 and get an integer? Yes, we can. We know that 4 times 3 gives you 12. And 4 represents your perfect square. Well, if you have an area of 4, what's your side length? 2. So the square root of 12 simplifies to 2 times the square root of 3, or 2 radical 3. Now let's take a look at the square root of 27. Again, where does 27 fall on your perfect square list, the area of your squares? That's between your 36 and 25. So again, we start with the one below. Can you take 27 and divide it by 25 and get your integer, whole number answer? No, we can't. So that's off our list. Can we take 27 and divide it by 16 and get an integer answer? No, we can't. Can you take 27 and divide it by 9 and get an integer answer? Yes, you can. So we're going to write this as the square root of 9, and we know 9 times 3 is 27. Well, if we have an area of 9, what's its side length? That's 3. And 3 is not a perfect square, and we cannot break that down anymore into a perfect square, so we're going to leave it as is. So we've got 3 square root of 3, or 3 radical 3. Why don't we try number 14? So we want to do the square root of 72. The area of 72 falls between 81 and 64. So we're going to start with 64 and work our way backwards, trying to find the largest perfect square area that we could divide into 72 and get an integer back. So can you take 72 and divide it by 64 and get an integer? No, you cannot. Can you take 72 and divide it by 49 and get an integer answer? No, you cannot. Can you take 72 and divide it by 36 and get an integer answer? Yes, you can. We know that 36 times 2 is 72. Well, if you have a square with the area of 36, what would be its side length? 6. So our simplified result would be 6 square root of 2, or 6 radical 2. We always want to go with the largest perfect square value because then it's only one step to arrive at our solution. Now, there are other perfect square values that we could use for 72. So some of you maybe said, well, I know I could take 9 and divide that into 72. Well, that's true. And let's see what happens. If you did that, that's 9 times 8. Okay? And we do know that the square root of 9 has a side length of 3, right? If the area is 9, the side length is 3. Now we have to work with the square root of 8. Now that falls between 9 and 4 on your perfect squares list. And look, 4 is a perfect square factor of 8. So we would have to break that down even more. So now we've got the square root of 4 times the square root of 2. And again, when you have an area for what's its side length? 2. So what do we have to work with here? Well, notice we now have 3 times 2 times the square root of 2. Well, what is 3 times 2? That's 6. And notice how we're back to where we were in the original problem by going to our largest perfect square factor. So again, this took us 3 steps to simplify, where this only really took us 1 step to simplify. That's the benefit of going with the largest perfect square factor. If you don't do that, it's not the end of the world. You can still keep simplifying, but you're always going to have to look at that radical and see, do I have any other perfect square areas I can use to break that down even more to be sure it's in its simplest format? Then we'll skip to our slide 22 here, and going back to how we were working with their unit originally, we were reminded ourselves that we were using right triangles to originally find the side lengths of our squares if we didn't know those, but we knew the area. So here we have our right triangle. We're missing a length of a leg, but we have one leg length and the hypotenuse. And the Pythagorean theorem says the sum of the 2 legs squared is equal to the hypotenuse squared. So if I take what I know about that and substitute in my values, my legs lengths are x and the square root of 3. So the sum of the 2 legs squared is equal to my hypotenuse squared. So if I'm squaring x times x, that's x squared. The square root of 3 squared, these are inverse operations, so they can undo each other. So we would have a 3. And 2 squared, 2 times 2 is 4. Some of you also like writing out the square root of 3 times square root of 3, thinking that it's the square root of 9. And yes, if the area is 9, that's also your side length of 3. It's still the same way thinking about it if we, instead of just undoing it from the start, this is just kind of the justification as to why we're ending up with that value being 3. So now we have x squared plus 3 equals 4. We want to undo this equation to solve for x. So our next step would be subtracting 3 from each side of our equation. So now we have x squared equals 1. Well, how do you undo something that's squared? You take the square root. So we're going to take the square root of each side. Now remember, technically, the square root of x squared, they do undo each other, and that leaves you with the absolute value, which means you're measuring the distance from 0. And when we take the square root of 1, 1 is a perfect square, and we know the side length is 1. So since it's the absolute value measuring the distance from 0, we have to ask ourselves, will going to the left 1 unit of 0 at -1 work for our scenario? Would going to the right 1 of 0 work for our scenario? And because it's a length, lengths cannot be negative. Therefore, we have to use the positive, so x is equal to 1. So that was just a brief recap of some of the practice that you'll be doing on your learning task 8.5 and a culmination of things that we've been working on from learning tasks 8.1 up to this point.